Hello guys, welcome back to my channel. So today in this next ASPEN Plus tutorial, we'll be working on reactors. Previously we have worked on PFR and CSTR. So in this case we'll be working on PFR with heterogeneous catalyst, and it is hydrogenation of CO2. So if you haven't watched my previous tutorials, I highly recommend you to go and watch it and then come back to this. I'll put that playlist in the near that I button. You can go and check it out. Okay, so the reaction which is taking place over here is that carbon dioxide plus hydrogen gives methanol plus water. This is actually a carbon capture, storage, utilization process where we use the CO2 captured from various applications. We store it under the grounds, and then we use with the help of hydrogen. The hydrogen can be produced from renewable energy using water splitting concept. So it's called as green hydrogen. And we use this green hydrogen to mix with CO2. We will be able to produce methanol and water, and this methanol can be used in various applications. So this is the basic reaction. So we'll be working on this reaction in the reactor. So the model which we are going to use here is SRK model, and the steam NBS tables will be using. I'll tell you what it is. And the model which we use here is LHHW mechanism. I'll also explain what it is. And we have the feed conditions over here. The component flow rates are given. The reactor's temperature, tubes length, diameter is given, and the rate expression is given. From the rate expression, you can verify that the reaction is not a simple elementary reaction, but it involves some intermediate stages with intermediate species forming. So it is a non-elementary reaction. But to work on this ASPEN Plus model, it's not required to know what are the intermediate steps involved, because we have directly given the rate expression. So let's quickly go into ASPEN and let's start the simulation. So open a blank simulation. We have to add the components. In this case, if you see, we have 5 components: carbon dioxide, carbon monoxide is present, but it does not participate in the reaction. So carbon dioxide, carbon monoxide, methanol, water, and hydrogen. So let's add them. Okay, so we have added all the 5 components: carbon dioxide, carbon monoxide, water, hydrogen, and methanol. So let's click on next. So here, as I said before, the thermodynamic model which we are going to work is SRK model. So SRK, and as I said before, by default we'll be using the steam TA tables, but in this problem they specifically given that we have to use steam NBS tables. So if you remember from your thermodynamics courses where you had used some steam tables at given temperature and pressure to find the vapor fraction, etc. Similarly, these tables work on different properties. We don't need to go into much details about it, but for time being, just know that we'll be using steam NBS tables than the default one. Okay, so let's click on next. So here you will be getting the binary interaction parameters which are estimated using Unific model, and by default the ASPEN has calculated the values to us, so we not change anything over here. So let's click on next and proceed forward, and let's go to the simulation environment. Okay, so we'll be working on the reactor. So go to the reactors tab and click on the plug flow or plug reactor, and now add the inlet and outlet conditions, and let's rename the steams as feed and products. Okay, and let's rename this as reactor. Okay, now let's double click on the feed and let's put the feed conditions to it. If you go back to the problem, it's given that 150 bars and 250 degrees Celsius. So let's enter the values 150, and if you see here, the total flow rate is not given, but in this problem we are given the individual flow rates of the components. So let's add them. Take care of the units. It's mole per hour. So let's start with CO. It's 4066. It's 4066 and change the units from kilomole to mole per hour. Okay, so we have added CO and carbon dioxide is 3976. 3976 and water and methanol are 0 because water and methanol are the products which are not present in the reactant side, and hydrogen is 28,920. So 28,920. Okay, so you have got a blue tick over here. So let's go to the main flow sheet again. Now we have completed the input to the feed. Now let's go into the reactor. The reactor type, if you see here, previously we worked on adiabatic reactor, but in this case the temperature is specified. So let's click on reactor with specified temperature and click on this constant at specified reactor temperature, and the temperature is given to be 250 in the problem. It's given as 250 and 8000 tubes, length is 12.2 and diameter is given. So let's go to the configuration and click on multi-tube reactor because we are having multiple tubes, which is 8000 in this case, and the length of the reactor is given 12.2 and the diameter of the reactant is the diameter of the reactor is given, it is 0.0375 meters. Okay, so before we go into the reaction tab, if you remember from the previous reactor problem, we went over here and we entered the reaction and then we came over here and added it. So we'll be following the same approach. So let's go to the reactions settings in the simulation window and click on new and let the ID be R1. And in the previous video where we worked on CSU and PFR, if you remember, we used the model called as power law model, but in this case we'll be using LHHW model. It is Langmuir model. So in this problem it's given to that we need to follow this, so we'll be using LHHW model. And let's proceed forward and click on new. So here we should be adding the reactants and products. CO2 is a reactant, reacts with hydrogen to produce methanol and water. If you see the reaction, there is carbon monoxide does not participate in the reaction, so we need not mention it in the reactant and product side. And if you see the stoichiometry, with respect to CO2 it is 1 and hydrogen it is 3. Since the reactants we have to put -1 and -3 respectively, and for methanol and water it is +1 and +1 because they are products. So for CO2 it is it's -1 because it's a reactant. For hydrogen it is -3, it is a reactant. Methanol it is 1, it is a product, and H2O it is a product, so +1. So we have entered the coefficient. Let's click on this next. And now we have added the reaction. Now go to the kinetics tab. Okay, so here since we are working on that LHHW kinetic model, there is an expression like R is equal to kinetic factor into driving force expression divided by absorption expression. Now let's focus only on the numerator part. So just ignore the denominator part. Okay, so in the numerator we have two terms, kinetic factor multiplied with driving force expression. Okay, so let's go and see the rate expression which is given. If you don't consider the denominator for time being, just focus on the numerator part. If you see here, we have K1 term multiplied with these bracketed terms, which means K1 is the kinetic factor and all the other terms are the driving force. Okay, so what we are going to do is that instead of writing this kinetic factor separately with the driving force, we are going to multiply this kinetic factor into the driving force expression, which means we will be multiplying this K1 into the brackets, which means we will be getting like 1 into the brackets with K1 multiplied. I hope you are getting. So in that case, the kinetic factor will become 1. I repeat again, instead of having kinetic factor and driving force separately, we will be multiplying the kinetic factor into the driving force. So which means that we'll be getting only 1 outside the bracket. So the kinetic factor becomes 1. So 1 is the kinetic factor, and K1 multiplied with this brackets becomes the driving force expression. And the E activation energy should be 0, because in this model we are not gonna use that power law expression, so E has to be 0. And now let's come into the driving force expression. In the driving force expression in ASPEN, it comes like term 1 subtracted by term 2. As the name suggests, it is a driving force, which means it should be a difference of something, some quantity. So in this case, this term is the term 1 multiplied with K1, and this term is term 2 multiplied with K1. Okay. So let's click on this driving force. And here, one more thing which you need to note is that the reacting phase is vapor in this case, because all the reactants are in vapor phase. So make it vapor, and now go to the driving force. And the concentration basis, since we are dealing with gases, it has to be the partial pressure of the corresponding reactant. Okay, so now let's type the term 1 first. If you see in the term 1, we have partial pressures respect to CO2 and hydrogen. It is 1, the coefficient exponents are 1 and 1. So with respect to CO2 it is 1, and with respect to hydrogen also it is 1. With respect to methanol and water it is 0. I hope you understand this. And now we have something called as coefficients A, B, C and D. Okay, so if you see the term 1, we have the coefficient of K1, which means K1 into partial pressure of CO2 into partial pressure of hydrogen. So for that, let me explain how are we getting that A, B, C, D parameters. For example, take a K is equal to K naught into e power minus EA by RT. This comes from the Arrhenius equation. And if you take ln on both sides, you'll be getting ln of K is equal to ln on K naught minus EA by RT. Here, this ln of K naught becomes the A, and minus EA by R becomes the B. Okay, so in this case, we are dealing with K1, because in the first term we only have the K1 term as a coefficient. So for K1, this K is nothing but the K naught, and E by R ratio is given. So this is K and this is E by R. So when you apply this concept, which means ln of K naught, which is ln of this value, is nothing but minus 26.87, and minus E by R is nothing but this value. You can see that this 0.76 is ignored, so it is for 4,413. We have used approximate value. Okay, so let's enter these values in the term 1 expression. So for the term 1, the A is minus 29.87, and the B is 4,413, and C and D does not have any value, so it is 0. Now we have completed the term 1. Similarly, we have to do the same approach to the term 2. So let's go to the term 2, and now let's see the term 2 as a partial pressure with respect to methanol exponent 1, with respect to water exponent 1, with respect to hydrogen exponent is 2. So with respect to methanol it is 1, with respect to water it is 1, with respect to hydrogen it's minus 2 because it's in the denominator, and with respect to CO2 is 0. I hope you understand. And now if you see the coefficient here, we'll be having K1 multiplied with KB1. So similarly we have to use this one. So we'll be taking ln of K1 KB1 is equal to ln of K naught, and ln for K1 also will be getting, for KB1 also will be getting, and we need to add the two equations. So if you do that, for K1 KB1, the A parameter which will be getting is 17.55, and for B will be getting minus 264.45.97. I am not doing this for time being. I hope you understand and you can try it with yourself. So let's type the values. It is 17.55, and the coefficient B is minus 2645.97, and C and D are 0 over here. So you can see that we have got a blue tick for the driving force. So let's click on next. Now let's focus on the denominator part. So go to the absorption. You can see here that we have absorption expression exponent. In this case, we have the exponent of 3 to the denominator. So this value becomes 3. And here we need to add all the 5 components. Let's add them over here. Okay. So if you see in the term 1, this is term 1, this is term 2, this is term 3, this is term 4. Okay, in term 1 we don't have any partial pressures with any components, which means everything becomes 0. Okay, now let's go to the term 2. If you see the term 2, we have exponent 1 with respect to water and exponent minus 1 with respect to hydrogen. So with respect to water it was 1, and with respect to hydrogen it was minus, with respect to hydrogen it was minus 1. Okay, and with respect to methanol it's again 0, and with respect to CO it is 0, and with respect to carbon monoxide it's again 0. Okay, so similarly let's see term 3. We have only with respect to hydrogen it is 0.5, so everything else becomes 0 over here. So with respect to hydrogen alone it is 0.5, and with respect to methanol again it is 0. Okay, so now let's go to the term 4. If you see with respect to term 4, we have only one exponent with water. So with respect to carbon dioxide becomes 0, with respect to carbon monoxide it becomes 0, with respect to water it becomes 1, with respect to hydrogen it becomes 0, with respect to methanol becomes 0. So we have completed this one. Now let's go and do the absorption constants. So we need to add all the 4 terms, term number 1, term number 2, because we have 4 terms in the denominator. Okay. Now if you see here, we have only 1 here, which means if you take ln of 1, it becomes A and B becomes 0. So coefficient A is 0, B is 0, it's already given. Let's go to term 2. For term 2, similarly as I said before, we have this K1 to term 2, K2 in term 3, K3 in term 4. We have to take ln of them. So we'll be getting the corresponding A and B values. So let's quickly enter these values over here. So we have entered all the details over here. So click on next. You can see that we have got a blue tick over here, but the required inputs are still incomplete. This is because if you remember in the reactor, we didn't add the reaction. So go to the reactor, go to the reactions tab and click on R1 and just add it. Now you can see that all the required inputs are completed. Now let's run the simulation. I hope we get no errors. Yes, so successfully we have completed the modeling. So let's right click on the outlet, go to results. So if you come down to mole flows, and let's add feed and let's add the products. So you can see that initially we had 36.962 kilomole per hour of the feed total, and in the products we have only 33.74 kilomole per hour. And you can see that carbon dioxide has reacted, so number of moles has reduced. The carbon monoxide does not participate in the reaction, so it remains same. Water, it was zero, methanol, it was zero in the feed, but they are formed in the products. And even hydrogen has reacted, so the number of moles of hydrogen also has reduced. So I hope you understand how to model a reactor using LHHW method. Thank you guys. So if you like the video, like it and share it and subscribe. Bye bye.